Hi everyone, today we have a lecture number 7. You remember that we have remarkable idea, aim to model financial market. We even made decision about assumption for this model. It's, you maybe remember, it's efficient market hypothesis, which states that there exist risk-neutral probabilities under some condition, which provide that discounted mathematical expectation of profit zero. And now it's time to think to see this thing in another side. We would like to find out how is such process called in mathematics, in stochastic processes. So today about stochastic processes, and our course is called stochastic processes and financial mathematics. So the main objective for today is to acquaint students with stochastic process and martingale. It's creating a culture of professional thinking in finance, development of analytical and forecasting abilities, and to create an independent critical attitude to market instruments and to introduce the features of their application. So at this picture you can see there's some trajectory, some paths of stochastic processes. For example, in red color, it is the first part, in blue color, it is the second, in green, the third, and so on. It is so you see that the value of stochastic process depends on not only time, but on random. So if we would like to give definition to stochastic process, we can say that it is a real value function. It's mapping of two variables. It is t and omega, and omega it is an outcome of stochastic experiment. And the value of this process, it's a real number. We can choose another way to define the stochastic process. For a fixed time t, stochastic process x is a collection of random variables. And really, you can see in this picture, if, for example, we fix t equals 100, yes, you see. So, so for 100, there are 1 point, second point, several points, and this point, it is the random value. So we can define stochastic process as a set of random value for every time. And there are another way to define stochastic process. It's for a fixed random outcome. X is a function of time. So it's a set of realization, set of trajectories, set of simple paths. So there are 3 ways to define stochastic processes. But if we stop it on the way defining stochastic processes as a set of random variables, you know from theory of probability how we can define a random value. To define a random value means to define the distribution function, yes? But how we can to define distribution function for the stochastic process? It's um, it's a vector for all possible choose of times t, t1, t2, tn, and every n more than 1 probability that this random value xt1, xt2, xtn less than a real number x1, x2, xn. It's called probability function. I think you remember this definition from theory of probability. Yes, Sophia, do you remember this? What is function probability in
Yes, yeah, I remember.
what is distribution function in theory of probability? Yes. But this dependence is very difficult, maybe impossible to define for real processes. So there are numerical characteristics and dependent structure for defining stochastic process. The numerical characteristic is very similar to numerical characteristic for random value. Um, the expectation function, the covariation function, and the variance function, dispersion. The expectation function, it is function, it's not random function, it is function which depends on t only. And I can see this for this picture. Maybe I choose. For example, we find the mathematical expectation for this point, and it will be this value. For this point, it will be this value, and after that, we connect this point, and for example, we have this function, and this function, it is mu from t. It's function of mathematical expectation, and we can call it as a trend. So we go on, and after expectation function, I would like to discuss the covariance function. Covariance function, maybe you remember too from theory of probability. It's mathematical expectation of product these values xt minus expectation and xs minus expectation. Yes, remember this formula?
Yeah.
And variance of function, it is sigma square. It is if you would like to define from covariance, it is covariance xt between xt and xt. So the difference in index 0. But we can define it in another way as mathematical expectation x minus mu square minus mathematical expectation square. But this characteristic don't define stochastic process totally, because you understand that there are the same mathematical expectation and variance, but the different properties of stochastic processes. For example, it is the same function of mathematical expectation, the same function in this picture and in this picture, and even variance may be the same, but stochastic processes um, can be very different. For example, in this it is this and this it may be different processes. So we should to choose another structure to define stochastic process. And for example, it's dependent structure. If we choose different dependent structure, we get a different kind of stochastic process. And from these kinds, we consider today the strictly stationary process. The process X is strictly stationary if the distribution function are invariant with respect to shift of the index t. So if we have the function of probability for this set of random values, and this distribution function for um, random values with shifts on index, this distribution function the same, and for all possible choice of indexes. And this process we call strictly stationary. There are two definitional stationary processes: strictly stationary and stationary in wide sense. If I would like to give the definition of stationary process in wide sense, it is the process which has function of mathematical expectation constant and the variance constant too. So in this picture, you see three stochastic process, and process in this in rows in pink color isn't stationary because the function of mathematical expectation isn't constant. It is a straight line. You see with angle maybe 45. Maybe 45. The process in orange color and process in green color, yes, its mathematical expectation function is a horizontal straight line, constant for any time 15, 20, 30, 45. The function of mathematical expectation is 10 for this process, and for example 5 for this process. But you can see that for process in orange color, the function of variance isn't constant, because in this part of time it is more, and this it is less. But in for blue color it can be constant. But yes, you're right, we need in additional researches, but from this picture we can say that it may be at least strictly stationary or stationary in white sense process. So from this picture, we can this say. And there are another structure. It is process with stationary increments. So if you have original process, for example, this process isn't stationary. But if we find the increments, so for increments process may be stationary. What is increments? I can explain. For example, we have original process, and the initial value is 0, after that S1, S2, S3, and so on. And for example, some last value S time 100. And we can find and we can find increments. It is for example, delta of h no, delta 1 equals S1 minus S0. Delta 2 S2 minus S1. Delta 3 similar, S3 minus S2, and so on. So if we have in this picture process ST, and if we find the first increments from this, we subtract this, and it's very little value, yes, and it is near around 0. And the second S2 minus S1, yes, you see, for example, it is S0, S1, it's S2, and we find S1 minus S0, it is a very little value but positive. S2 minus S1, it is very little too but negative. So the picture from increments will be on the picture too. Do you understand how we can find and draw increments, Sophia? Sophia, did you understand? Is it clear?
I'm not sure about this.
Repeat.
I'm not sure about this.
Why? What is question? We have I can explain again. We have this stochastic process, one of realization, yes? And we have this value S0, S1, S2, S3, and so on. And after that, we built another process according to the rule that delta 1 is difference between S1 and S0. Delta 2 is difference between S2 and S1. Delta n is difference between Sn and Sn minus 1. Did you understand?
Yeah.
And it will be graph of original process, and it will be graph of process of increments. Yes? Is it clear, Sophia?
Yeah, but why is it called log returns?
Why is it called returns? Returns because it's as profit as returns. So
and after that we take the logarithm. Yeah.
yes, but no, it's another. But in the theory of stochastic process, increments it's difference.
Yeah.
Difference, and you see that if we have trend in this picture, if we have the function of mathematical expectation on this picture, this trend is zero. Is zero.
Yeah, I see.
Thank you. And we could say that this process may be stationary. It is we are not sure that this process is stationary, but it's maybe. But we need additional researchers. And so the second dependent structure, this second summary, yes, the second dependent structure, it is the process with stationary increments. The original process not stationary, but its increments is stationary process. There are another dependent structure. It is the process which have independent increments, independent. So, so we find increments as I explained. For example, this delta 1, delta 2, and finally delta n. And all these increments are independent random variables. How we can check it? For this, we can check that these increments correlate on or uncorrelate. For this, we can find covariance, and if this covariance will be zero from all index I isn't equals g, so these increments are uncorrelated. But if we would like to check independence, so should be have be uncorrelated not only this delta, but delta in square, delta in cube, for square root from delta. And so if we, for example, and how we can find it, it is we built autocorrelation and special autocorrelation function. Just a second. It's not difficult. It's not difficult, but it takes a time for explain in detail. But now only first concept. And for processes with independent and stationary increments, we can distinguish the Poisson process and Brownian motion. It's widely applying processes, very important processes. This process, it is yes, it is processes with independent stationary increments, and that process has three properties. In initial time, the value 0, it has stationary the independent increments, and the distribution for any t, it is Poisson distribution with parameter lambda t. And very important Brownian motion of Wiener process. It starts at 0, 2 as Poisson process. It has stationary independent increments 2, and for every time t more than 0, this process has normal distribution with mean 0 and variance t. And in addition, it has continuous sample paths and no jump. And after that, we would like to stop on the martingale. We can hear about martingale in three ways: is a Tarkov strap, is a betting system, and is probably theory. So we interested in martingale in probability theory. It is a stochastic process in which the conditional expectation of the next value given the current and preceding values is the current value. And you see that maybe it's is recalled you about our efficient market hypothesis that the mathematical expectation, yes, of the next value is the current value. Thinking if we denote this process martingale as m sub n, and thinking of mn as the amount of money at time n for gambler betting on a fair game, we say that this sequence, it is a discrete time martingale. If for any n more than 0, we have two conditions: mathematical expectation less than infinity, and for any possible values m little 0 and m n, we have these properties that the conditional mathematical expectation equals the current value. So we know all information about value for a moment n. For moment n, we will all information begin m0, after that m1, and for moment n we have m little n. All information we have, but mathematical expectation for the next value, if we have all this information, it is the current value and little n. Um, but this condition is needed to guarantee that the conditional expectation makes sense. And these properties we can rewrite as the difference, And in this case, it will be 0, and it is very similar to definitional of efficient market hypothesis that the profit, mathematical expectation of profit is 0. You see, yes? And in this slide, you can see the definition of martingale process in previous for discrete time, but this it is as a process for continuous time. But it is very similar. We have the two conditions. The first condition guarantee that mathematical expectation made sense, and the second states that the condition of mathematical expectation, if the all information for moment n is known, so the mathematical expectation is this current value xn. But there are another process, sub-martingale and super-martingale. In this process, this mathematical expectation more than xn or less than xn, and this game isn't fair in this case. But if we guarantee that it is equals, so it is fair games. But if the mathematical expectation at the next moment is more than this value, for example, we threw a coin, and the mathematical expectation may be the next moment more than at this moment, it's not a fair game. Yes, you understand. So risk neutral measure, it is measure which guarantee the fair game. And for example, in this example,